All right, this is where we left off, talking about computational complexity. And you remember from before, when we were doing computational complexity, like trying to figure out like the big O of something. Oh, like, is it linear? Is it quadratic? Is it logarithmic? Is it constant? Like one of the tricks that we did, like at this stage, the tricks is we looked right at the loops. And the question was, how many times did that loop run? And, oh, you can't see anything. Let me fix that. Why didn't you say anything? Just wanted to see how long I'd go. There, am I recording? Good. There, that's better. The trick was look at the loops. How many times did the loop run? If it's a for loop, it looks like it's going to run n times. It's n, right? It's linear. If you had nested loops, you start thinking it's quadratic, right? N times n, n squared. It's the same idea when doing computational complexity for recursion, because at the end of the day, when I say how many times does the loop run, really what I'm saying is how many times is this chunk of code going to have to run? That's what I'm getting at there when I'm saying looking at the loops. The same idea happens here with recursion, like in the factorial example, right? Factorial. If I said, let's go look at the code. Right? This one in particular. When you look at the iterative version, actually, let's look at this. Yeah, you look at the loop. Sure, it starts at 1 and it goes to, it's going to run n times. So whatever n is, it's going to run n times, right? But what's the computational complexity of this recursive one? Well, how many times is this loop going to run? And if you're thinking like, well, how the hell am I supposed to know? Well, what does the code say? If I give it n, how many times will this loop run? Don't even worry about being that precise. Will it run roughly n times, let's say? Well, think about it. If I gave it n as some arbitrary value, it's going to run for n. Then it's going to run again when it's n minus 1, n minus 2, n minus 3, yada, 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 2, 1, 0. So how many times is it going to run? N. Think about it like this. If I put in a 10, I started at 10, n will start at 10. The next time it calls, it's going to get called with 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. You might say, oh, it's n plus 1 times. Remember, I don't care. I don't care about the plus 1. It's n. It's linear. So it all comes down to how many times is this code going to run? How many times am I going to call the recursive thing? That's the trick when looking at the computational complexity of recursion. Really anything, but recursion specifically because, no loops. So yeah. It's important to think about how many operations will be needed relative to the size of the input, n. Further, it's important to think about how much amount of work is getting done and how it scales relative to n and how n changes. So looking at iterative factorial, we know it's n because, okay, well, what do we have here? Iterative factorial. There are a few constant time operations, don't count on n. So the iterative factorial, like this is constant time, right? Like really it's just that and setting up the for loop. Then there's the loop that's going to run like n times, n work, big O n. The recursive, well, like I just said, there's some constant time stuff, but the recursive call is going to get called for n, n minus 1, n minus 2, and so on. That's what I'm saying. So here's a little table to kind of show you what I mean. How many times does it run? Well, if I give it n, it's going to call it for n, and it's going to run it again when it's n minus 1, n minus 2. I'm just keeping tabs on how many times I've done it, and as you can see, we count to a total of n plus 1 things. So with input n, recursive factorial runs a total of n times. It's linear. It's order n. Any questions about this idea of computational complexity? Now, you might say, well, I knew it was going to be n because the iterative version was n. So if the iterative version's n and recursion and they're the same, it's going to be n. Well, sometimes it's not that simple. Fibonacci. Who here has heard of the Fibonacci sequence before? Where'd you hear about it? Did I tell you about it? I did. All right, fine. There it is. That's it. That's the Fibonacci sequence. Raise your hand if you know how to generate the Fibonacci sequence. Really high, I want to see. Okay. Raise your hand if you don't know how to generate it. And it's fine if you don't. Okay, perfect. I want you to take a moment. If you don't know what the hell this sequence is, if you do know what it is, keep your mouth shut. All right? If you don't know what it is, try to figure it out. Try to figure out the pattern. What were you going to say? Don't answer it. I'm not asking someone to answer it. I want you to look at this and think about it for a moment. Or did you have a question? No. You were just going to answer it. Okay. We'll come back to you after a minute. I will give you a hint if you don't know. Here's the hint. 0, 1. That's the hint. As you can see, the hint is actually just showing the sequence, but I'm doing it like only one number at a time. So there's the hint. Well, raise your hand if you didn't know how to generate it, but now you know by looking at it. Okay, raise your hand if you still don't know. Be honest. Okay, I'm going to wait a little bit more. You start with 0, 1. That's it. And again, as a note, I've got my mic plugged into my computer today because of the battery. If I start wandering too far, let me know. All right, so what is it?
It's the last two consecutive terms generated added together.
Exactly. You take the last two numbers, add them together, and then tack on the sum. That's it. It's a weird sequence, though, right? Because you're used to, like, describing a series with some basic closed form expression, right? Like n squared plus 7 divided by 2. And you can generate, like with a function, you can generate what the values will be, right? But this one's a little weird because it's actually very like, oh, it's the sum of the previous two. It depends on what came before it. It's interesting, right? So 0, 1. If you add 0 and 1 together, what do you get? 1. So when you add 1 and 1 together, what do you get? 2. You add 1 and 2 together, you get 3. You get 2 and 3, you get 5. 3 and 5, you get 8. What's 5 and 8 added together? 13. Well, that better be the next number. And it is. Yes?
If you started off with, like, say, 2 and 5, would it also be the Fibonacci sequence if you followed the same pattern?
No, but yes. So no, it's not the Fibonacci sequence. This is the Fibonacci sequence, but it's going to have that same idea. And there's a whole bunch of these ones that are very interesting and fun. And there's actually a lot of like really interesting things that you can see with the Fibonacci sequence. Let me just see if I can show you a quick example. I don't, oops. Fibonacci numbers. Let's see if I can just find like a nice image, right? Because you can kind of, there, all right? So here's like a nice little image that kind of shows you like, oh, you can get this nice fun little spiral, right? Just open a new tab. And you can kind of see how like, well, okay, starting with 1, 1, you start with this like a square that's 1 by 1, you add them together, you get a 2 by 2, and you stack it there, then you take the 2 by 2. So you take the two sides and you make the new, anyways, I don't know, I think it's kind of neat. So anyways, that's the Fibonacci. There we go. Great, cool. So any questions about this? There's like a story that goes with it about bunnies multiplying or something. I don't know. Like if bunnies are on a desert island, this is what happens. Something like that at least. I don't remember. But any questions about it? All right, so now that we see the pattern, well, how can we describe this mathematically? Or well, here's how we could describe it with code iteratively. Okay? Take a moment, look at this code. I'm going to give you all a moment. I'll keep my mouth shut. Take a moment, look at this code, make it make sense to you. Oh, I didn't ask a question. Do you have a question?
Yeah, I just don't understand why the I is equal to 2.
Why it starts at 2? Oh, that's just like the edge case stuff, right? So if n is 0, the answer is 0. If n is not 0, but it's 1, right? Well, then it's just whatever current is. Because the
Oh, okay.
0, the 1th Fibonacci number is 1. It's just like the edge case stuff. Yeah.
So is n just how many digits?
Like we want the nth Fibonacci number. Yeah. So if I say 7th, I want, okay, 0, 1, 2, 3, 4, 5, 6, I guess 13. I want 13. Here's the pattern. All this is doing, the loop is the important part. We start with, okay, if n is 0, it's 0, right? Then we say, okay, well, previous, will be 0. Current is 1. And next I have a 0, but that's just some default value. It doesn't really matter what it is. If n is 1, 2 is not less than or equal to 1, so we just skip the whole loop and return current. We get back 1. 1 is the 1th Fibonacci number. But when it's bigger than that, what do? Well, we just say next is the sum of these two, and then we move them down. Then we say previous becomes current, current becomes next. Add them together. This becomes 2, and then this becomes this. I'm not going to do it. And then this becomes 2. Add them together, you get 3. Move them down. 2. That's the pattern, which is basically what we were doing, right? When we follow the numbers on that line, we're just kind of like changing what we consider the previous and the current, right? So when you look at this code, don't look at that, there. Look at this code. What's the computational complexity of this code right here? It's not a trick question, it's just a, n. Why? Well, we've just got a loop that's going to run linearly. It's linear, it's n. If I want a Fibonacci number that's twice as, like, I don't want the 10th Fibonacci number, I want the 20th, well, I got to do twice as much work. If I want the 40th, I need to do twice as much work. It's linear. Cool? And is this code more or less clear? Like, you've got the idea. The idea is just kind of like shuffling down what's in these variables there. Yeah. Any questions? Ask now before I go to the next thing, because the next thing's more fun. All right. So, I mean, here's how we define it recursively, mathematically. The nth Fibonacci number, well, if n is 0, it's 0. If it's 1, it's 1. And if it's greater than 1, well then it's the sum of the n minus 1th Fibonacci number plus the n minus 2 Fibonacci number. In fact, I'm looking at this iterative version. I'm thinking maybe I should have cleaned it up a little bit to kind of get to your question, like why start at 2? Maybe I should say n is 0, return 0. If n is 1, return 1. Maybe that's a little clearer for the iterative version, but whatever. Yeah. But here's like the recursive definition. Is this, don't worry about the code right now. Look at it like the mathematical one. Any questions about this one here? Like it's a conditioned expression. If you're not familiar with that, you can do that in math sometimes. When n is 1, or when n is 0, it's 0. When n is 1, it's 1. Otherwise, it's the sum of, if I want the nth one, for example, if I want the 10th one, it's the sum of the 9th and the 8th. Cool? Cool. And here's how we can write that in Java. If n is 0 or n is 1, return n. Basically, if n is 0, return 0. If n is 1, return 1. Right? So if it's 0 or 1, return the 0 or the 1. Otherwise, return Fibonacci, recursive Fibonacci of n minus 1 plus recursive Fibonacci of n minus 2. When you look at this code, here's the iterative one. There's nothing wrong with it. We kind of talked, maybe we can improve it, clean it up a little bit, but there's nothing wrong with it. But here's the recursive one. Which one do you like?
Recursive.
That's the correct answer, yes. Maybe you don't like the recursive one, I don't know. But to me, raise your hand if you have if you feel as if you might have the remotest of idea of what I mean when I say like there's something like elegant about the recursion, right? Like there's like an aesthetic to it that's just like, ooh, that's nice. There's like a beauty to it, I don't know. And what I really like about it is it's so, it's succinct. Let's use that word, succinct. Which I realize is like, it just means short, but it sounds better, right? Like, it's to the point, it's brief, but it's accurate, it's precise, it's nice. And it's so like, it lines up like beautifully with the mathematical description right there. It's the same. No, it's because that's a recursive definition, and this is a recursive definition, but using Java notation instead of just our common math notation. So, to me, let's do a quick poll. Raise your hand if you're like, yeah, the recursive one isn't clearly nicer, right? So raise your hand if you disagree with that statement. You're like, I don't know. What makes you, your comfort with recursion, okay. Or maybe you're just really smart and you're onto something. And everyone else, they just didn't realize it yet. What's the computational complexity of this? Constant? It's not constant. I want everyone keep your mouth shut. You can talk to each other, but if you know the answer, don't yell it out. Take a moment. I'm going to give you a few moments. Look at this code and think about it. Right? Let's do a quick review. Here's factorial. How many times is recursive factorial going to get run? Well, if I give it the value n, it's going to run once for each of those n values. So it's linear, right? There's no trick question here. What's the computational complexity of recursive Fibonacci? You can talk amongst yourselves, just no yelling out the answer, no yelling out what you think the answer is. Either way, I'm going to give you a few moments to really think about this one, because you are all absolutely capable of figuring this out. Just don't try to do any shortcuts, just follow the steps. How many times will this code get run? For this one, when you know, you know. All right? I'll put it that way. And then if you know, you know. All right, who wants a hint? One person. Well, I'm going to give everyone a hint anyways. Here's the hint. Ignoring the base case, we're thinking of the general case, the recursive case. So I give it some arbitrary value n. Every time I call this function, how many more times is this function going to get called? It's a simple question. What were you saying? Twice. Exactly. And if I call it once, and by calling it once, it calls it twice. And then for one of those two times, it runs. How many times does it call the function? Twice. And this time, how many times does it call the function? Twice. And that one will call it twice. And that one will call it twice. Take a few more moments to think about this. Here's another hint. It ain't linear. It's worse. Okay, I'm just going to do a poll. Raise your hand if you have an idea of what it is locked in. You don't have to be 100% confident about what you think, but if you're like, no, I've got an idea. Really high, I want to see. Keep it up. Okay. Keep your hand up if you want to take a stab at it. What do you think?
Thinking n squared.
N squared? Not quite. It's a little worse than that. I want to see. What were you going to say? 2 to the n. Raise your hand if you were like, yeah, I was thinking 2 to the n. That's what my idea was. Yeah, 2 to the n. You were close, you just had to flip it. 2 to the n. Why is it 2 to the n? Well, to be clear, I don't want to, when I'm done this topic, I'm not expecting you all to leave this room with a complete, pure, 100% brilliant understanding of why this is 2 to the n and you'll never get this wrong ever again. No, you learn that next year in way more detail. Right now, we're going for the abstract, intuitive understanding as to why. All right? And there are a couple of ways I can try to give you this intuition, but let's just take a moment and think. I'm going to call, well, no, maybe we could just use what's already here. So 2 to the n. We start with 1. And that 1 spawns 2. And those 2, each of those 2 spawns 2, meaning we get how many? 4. I'm doing it backwards. I'm getting ahead of myself. And each of those 4 spawns how many? giving us 8, which gives us 16, 32, 64, 128, 256, 512, and so on and so on. It's doubling every time. So every single time we double. Every time the function gets called, we double the amount of work. And the pattern of doubling, well, that's 2 to the power of n. Okay? 2 times 2 times 2 times 2, however many times we want to multiply by 2. So you at least have the idea as why it's 2 as the base. But why is it to the power of n? Well, think about it, right? We start with n, 1, n minus 1, 2, n minus 2, 4, n minus 3, 8, right? Like for every time, like we're getting smaller. Eventually we're going to hit 1, 0, and that's how many times you want to double, right? That's loosely the pattern we're following here. Now it's not 100% this, because, well, it's actually every time we go down, we're not doing minus 1, we're doing minus 1 and a minus 2, like this. When I call Fibonacci for the 6th Fibonacci number, I need to calculate the 5th and the 4th. In order to calculate the 5th, I need to know the 4th and the 3rd. In order to calculate the 4th, I need the 3rd and the 2nd. In order to calculate the 3rd, I need the 2nd and the 1st. And so on and so on and so on. So this is how we could draw out, this is how we can visualize all those function calls. So to be clear, it's not actually as bad as an upper bound of 2 to the power of n, but the computational complexity of this right here is 2 to the power of n. Now, do you remember like when we talked about computational complexity like a month ago, I was saying there were a couple of like important ones that we look at, right? We can get really nuanced, but we have like constant, logarithmic, linear, n log n, quadratic n squared, and so on, right? Where does 2 to the power of n fit in the hierarchy of badness? It's really goddamn bad, right? If someone says to you, I've got a linear time algorithm to calculate the nth Fibonacci number, and someone says, no, 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 I've got a better one. I swear, it's 2 to the power of n. No, 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 that's terrible. That's horrible. That's horrible. But, look, the question is, why is it worse? Why was the iterative version that I showed you linear, and the recursive one 2 to the power of n? What's going on? To be clear, I showed you 2 very different algorithms. When I showed you the iterative factorial and the recursive factorial, the underlying algorithm is the same. It's coded entirely different. One's recursive, one's iterative. But the actual algorithm, it was the same algorithm. And remember I said like, oh, you know, recursion's kind of slower. That's not what's happening here. It's not that recursion is slower. Recursion's only slower because of the consequence of how your computers work, not because it's fundamentally slower. I want to be very clear that the iterative version of Fibonacci and the recursive version of Fibonacci, the 2 versions I showed you, are actually 2 very different algorithms. Not because one's recursive and one's iterative, sure that's the case, but because the actual algorithms used were different. So they're different complexities because they're different algorithms. But like, what is it about the recursive Fibonacci that I showed you that made it so bad? Why is it so much worse? Like, what is it about it? There's something about this function that must make it worse. And this image should give you a good hint as to what's wrong. What do you think?
Is it that it calls itself twice?
Well, it's calling itself twice. That is, like, the problem. But what is, like, that's it's connected to the core issue, but it's not quite the core issue. What were you going to say?
It's calculating the same value like a bunch of different times. Like it says Fibonacci of 2 like 8 times there, something like that.
So to calculate the sixth Fibonacci number, with the iterative version, how many times did it calculate the second Fibonacci number? Once. Here, 1, 2, 3, 4, 5 times? 5? 1, 2, 3, 4, 5. Looks like 5. Am I miscounting?
See,
5, maybe, okay, 5. I'm repeating a lot of the same work. And that's a problem. That's the core issue, is we're doing the same work over and over again. It might not feel that bad when I show you a picture with the sixth Fibonacci number, but imagine I showed you what this tree would look like with the 60th. What's 2 to the power of 60? Someone type that into Google real quick.
One great big number. 5 times 10 to the 18.
Times 10 to the 18, that's a lot. That's a lot. And that's like the amount in the bottom row, not even like in total, right? So you have to do it like one more time, but it's a lot of work. You want to know, here's an aside, right? You want to see an interesting pattern. This is not directly related to what I'm showing you, but it's not directly about what I'm showing you, but it's an interesting pattern that's very related to what I'm showing you, and this pattern's going to show up a lot, and I kind of want you to notice it. I'm going to draw this situation, right? How many things are in this bottom row? How many nodes are there in total, not counting the bottom row?
7.
Ignore the bottom row. How many are here? 4. And then how many are here? 3. The number of nodes in any tree, we call this a tree. In any tree like this, a binary tree, if it's full and complete like this, the number of nodes in the tree, there's always a relationship that the number of nodes in the bottom row is the same number as the number above it minus 1. Which is kind of neat, right? If you think about it, you can figure out why. Because how many would be in the next row? 16. And then 8 plus 7 will be 15. Right? So interesting pattern, right? Anyways. Yeah.
So is it this portal because it's going from the top down as opposed to the other one where it's building the values on?
It's not even that complicated. It really is just because the way it's written. When I say, tell me the sixth Fibonacci number, it needs to calculate the fifth and the fourth. And when I want to calculate the fifth, it needs to calculate the fourth and the third, and we just calculated the fourth twice. It's all about the number of times. And to be clear, we could make a recursive version that doesn't suffer from this problem. But that's far less interesting to talk about, right? This is just, explaining it. It follows a pattern of 2 to the n. In other words, it's this recursive implementation is big O of 2 to the n. If given the choice between something that grows linearly or something exponential, don't take the exponential one. So this would be an example of, despite the simple beauty and elegance of this one, don't use this one. Don't do it. This is bad. Very, very bad. I mean, does anyone have like IntelliJ open and running and ready to go? Try calling this function with like 100. See how long it takes. No, you know what? I think this could be a good... So here's what I want to do. I'm just going to create like a new dummy program, and I'm just going to call this Fibonacci function. And we'll give it a few goes. Let's just do like, do I have? It's poor computer. You can do it. Source. I'll just go to lab 2 because I know it's got a main in there. Perfect. Okay. So let's calculate the 6th one. It's not too bad. Shouldn't take a long time. You should get an answer just to make sure everything's working and running. This is ridiculous. It's going to take a hell of a lot longer to start running. There we go. It's 8. Great. Let's hit run again so we get a sense of how long did it actually take to run. It's rebuilding everything. What's going on? This poor computer. Whatever. It's like once it actually starts running, it's pretty fast. So that was the 6th. Let's get like the 10th.
Mine didn't take that long. Your computer's just this long.
55, right? That was pretty quick, right? 20, right? You know, if it was linear, 20, that should take twice as much work. Remember, all of that stuff, you know, there we go, that's not too bad. Better not be doing tail end.
Yeah, mine did it almost immediately. I think Java's optimizing it.
Is it really tail end optimizing?
Because
Fibonacci?
I did 20 and it took like a second.
We'll try like 50.
And seeing it now, and I got it. Wait, no, it's wait. And now it's going to go.
So 2 to the, what's 2 to the power of 30?
Big number.
Big number, but it still got it pretty quickly.
2 to the power of 30, that is 1 billion-ish.
1 billion, yeah, that makes about sense for computers to be doing that many, you know. What's 2 to the power of 40? I bet you,
1 trillion?
that wasn't instant anymore, was it? Took a couple milliseconds, let's say. It's 50. What's 2 to the power of 50?
Just add 3 more zeros to 1 trillion. Or half a trillion.
Yeah, it's starting to
Yeah, mine finally found it.
starting to take a second here, isn't it? If you're watching the YouTube video later and the video starts like really chunking, and this is why. It's because the computer's trying to record video and calculate this very important number that we're doing in a way that we know is terrible and is going to be hard for the computer. I'm actually curious. Later, I'm definitely going to go check the video at this part to be like, did the video like go to shit? Like, but look, it's still running. And it's funny because it figured out 40 like in like what, a second? So 50. Still going. Still going. If this was linear, it should have taken just a little bit longer. Now it's still thinking. I wonder where it is. Should I just stop it or should I let it keep going, right? Like, I don't know. What do I do? Well, we'll leave this. Let it do its thing. And we'll carry on. Yeah, so there we go. Da, 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 there we go. So yeah, and then the iterative version, it only had to calculate it once. So, are there any questions about what we just saw? I know everyone's they're just like waiting for it, right? You're not even listening to me anymore. You're like, come on, you can do it. And if you're thinking, well, his computer's just old and slow, fine, fair. But, yep, hey, oh, does that look right?
Maybe you have to make it like long.
Yeah. Who wants to guess what just happened?
The number's too big for me.
The number's too big. We didn't have enough bits. The integer wasn't enough. We needed to use a long. Remember in the first assignment how you had to use a long for the constant populations? If you didn't, this is what would happen. You'd have an integer overflow. Does anyone ever hear that phrase before? Let me show you real quick. If I had, computers work with bits, right? Zeros and ones, low voltages and high voltages. And what's really interesting to note about the zeros and ones, right? When we talk about binaries, we're always thinking, oh, binary number. But you gotta really realize that binary is just the patterns of zeros and ones. Binary doesn't mean numbers. Binary is just the zeros and ones. And what the zeros and ones mean all depend on how we decode them. But if we're decoding these as integers, for example, let's say we had 8 bits. The same problem is going to exist with 8 bits as it is with 32 bits or 64 bits. In Java, an integer is 32 bits, I believe. Could someone just double check that for me real quick? How many bits in Java?
32 bits.
32 bits, there you go. And then a long is going to be 64. If we used a long here, it would have been 5. Now, if I had 8 bits, that means I have a series of 8 zeros and ones. 0, 1, 0, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, right? And that would be a number. I don't know what it is. Okay, let's see real quick. 0, okay, 1, 2, 4, 8, 16, 32, 64. That's 64 plus 1, 2, 4, 8 plus 3. Well, 2 plus 1. So 64 plus 8 is what?
72.
72 plus 2, 74, 73. So this is the number 73, only because I decoded it as an integer. So when I have 8 bits, though, the biggest number I could represent, assuming this is an unsigned integer, the Java ones were signed integers, as you read, but let's assume it's unsigned. That means I have 1, 1, 1, 1, 1, 1, 1, 1. And what is that number? So what is that? 64, 128, 200, 254. That is the number 254. And you know, yeah.
Explain again, sir. I used space out for a moment.
Sorry, what was the question?
Could you explain again that part?
No. You can watch the video. That's 254, because we're running out of time. Now, the way we count in binary is the same way you count in decimal. In decimal, we go, okay, 0, 1, 2, 8, 9, and what comes after 9? 10. But, nailed it, right? Yeah. So, well, that's, you're like, yeah. So, but we don't have a symbol for 10, do we? We use 2 symbols to mean 10. We use a 1 and a 0. There's no one symbol I use for the number 10. Unless we're doing hexadecimal and we use the letter A. Let's ignore that. So what do? We go back to the beginning. And remember, what comes before the 0 here? The 0. Hell, there's an infinite number of zeros, right? So this is like 0, 0, 0, 1, 0, 2, 0, 8, 0, 9. So what do when we run out of symbols? We restart and increment the next symbol. So this becomes, I'll just draw it up here. The 9 turns into a 0, and the 0 turns into a 1.
Crazy stuff.
Counting, right? I know. Holy shit, this is crazy. You should all be very well aware of how this works. It's weird to me that I have to explain this right now. Eventually, this, like, I'm gonna hit like 19. Oh, I'm out of symbols. What do? I start over, and I increment this number. It becomes a 2. And then eventually, I get to like 99. Oh, I start over, increment, well, I just start over again, and I increment the next one. That's how counting works. Hopefully you're aware of this. In binary, it works exactly the same way, but the catch is, instead of 10 symbols, and yes, I said 10 because 0 is a symbol, instead of 10 symbols, we have 2 symbols.
It's called binary.
0, 2. 0, 1. So if I start with 0, and what comes after 0? 1. What comes after 1? Uh-oh. We got to start over. But we increment the next one, and then we do it again. And then we got to start over. Oh, we got to start over. So it's the same pattern. If I add 1 to this number, what happens? Well, that becomes a 0, 0. Oh, no, right? Well, so this would just become 1, 0, 0, 0, 0, 0, 0, 0, 0. But we got a problem. The computer's only holding 8 bits. We need 9 bits to store the number 255. This is 255 when you decode this string as an integer. I need that 9th bit. It's not possible for me to store the number 255 in 8 bits. So as far as the computer's concerned, this number just vanishes. The 9th bit doesn't exist, it's gone. So the number that comes after 254 is, of course, 0. It's the same issue you would have if I said, what's the biggest number you can store, but you only have 8 decimal places? Well, that would be 999999999. If we're limiting the amount of space we have, we're limited. So that's what we just saw there, is we had an overflow issue. It overflowed. Oh no. This plagued video games for a very long time. The kids these days, living in a world with 64 bits, you got it made. You don't have any bosses that are unkillable. Or you don't have any bosses that are easy to kill because they're damn... Anyways. That's it. We'll stop here for now.